All right, so hello everyone. I'm Abderrahim Halimi, Assistant Professor at Heriot-Watt University and Research Fellow from the Royal Academy of Engineering. And today we'll be talking about recent statistical-based methods that we propose to reconstruct 3D LiDAR imaging. Okay, so this presentation deals with advanced imaging systems that we find more and more in our life, whether it's 3D imaging to help navigation or in our mobile phones, or medical imaging, such as in MRI. And in most of these imaging systems, we often see two main challenges. First challenge is the large volume of acquired data. And the second one is the extreme conditions associated with real-world measurements that leads to often corrupted and noisy data. So to deal with these two challenges, we mainly have two directions from a computational point of view. The first one is to improve the acquisition by adopting comprehensive sensing strategies or task-based adaptive sampling. For example, if we want to optimize the reconstruction of this 3D face, we will put more samples around the small features of this face to improve the quality. The second direction is to improve the processing of the data by adopting robust models and designing specialized algorithms, which can be statistical, deep learning methods, and the goal being to reconstruct a better version of the scene, moving from this noisy 3D representation to something clean. And the ultimate goal actually is to optimize both aspects in the same time, to have smart systems that deliver robust estimates, reliable estimates, where we have some quantified measure of the uncertainty of these estimates as well. So in my group, we propose different solutions in both directions, but today I will be talking about the processing side. And this is the framework that I will follow. I will assume that I have some input. We will design algorithms that take into account guiding information to provide us with some output. More precisely, as input, we consider that we have LiDAR data. In terms of algorithms, I will be talking about statistical algorithms and how we can enroll these into a network to solve problems related to 3D reconstruction of highly dimensional data, such as 3D videos, and how to perform super resolution. All that while taking into account some side information that we might have from other sensors or other algorithms. So here's the outline of my talk. First, I will describe the input, which is the LiDAR measurements. Then I will describe two frameworks, the statistical algorithm, and then how we can enroll it to obtain a hybrid algorithm. So how does LiDAR work? The Single-Photon Lidar allows us to acquire 3D images of the scene, and that's happening by sending laser pulses that get reflected from target. I'm having a hard time to control this pointer, but bear with me. So we fire photons on this target, they get reflected and then captured by a very sensitive detector. We called it single photon detector because it's able to measure photons together with their time of flight. If you know the time of flight of the photons and you know the speed of light, you will be able to deduce the distance between the system and the target. So we repeat this experiment measurement in different locations of the target, and this allows us to build an array of measurements where for each point, we can obtain a histogram representing the number of photon counts that we obtained with respect to their time of flight. So in ideal situation, we will obtain a nice peak like this one, where this position here, this position indicates the distance between the target and system, and the amplitude of the peak informs us about the reflectivity of the object. Obviously, in real life, we don't see that. We often see this scenario of sparse photon regime as we only receive few photons from the target. And here again, the goal is to estimate the peak associated with these photons. As we do measurements through an environment, we might obtain photons coming from the sun if the conditions are bright, as you can see outside. the sun will be firing photons that will be also catched by our detector as uniformly distributed photons that will hide our target. The situation can be more difficult if we are doing imaging through obscurants, such as when doing underwater imaging or when imaging through smoke, in which case we might obtain non-uniform background represented here by this red curve, and it can be quite high to hide our useful peak. So this shows what kind of corruptions can affect our data. In parallel to that, we also have a challenge related to the volume of data, and this appears more when doing multispectral LiDAR imaging. So when firing light with different wavelengths, and in each case, we'll obtain a cube of histograms associated with each wavelength, and then we want to process all these cubes jointly, and this constitutes a huge data. Okay. Yes, and another challenge is when having other systems looking at the same scene. So we can have our LiDAR together with a radar, a passive RGB camera looking at the same scene, and we want to take all these measurements and to extract maximum information from them. So these are the issues or challenges that we'll be dealing with in this talk. And first, let's see how we can solve the problem using statistical model. So now the framework is that we have this LiDAR data, and we will design statistical method that estimates parameters together with their uncertainty, while taking into account guiding information that we might obtain from other sensors or other algorithms. And the key observation that we had done to improve the processing of this data is the following. If you plot the 3D histograms that we measured in 3D, this is what we see, which is quite a noisy cube. Now, if you do maximum likelihood estimator based on Poisson statistics of this data, we can obtain this depth map representing the distances of the object and this reflectivity map. And what you see here is that the images are quite noisy. So if you take the raw data, the reconstructions or the estimates are quite noisy. Now, if you low-pass filter this raw data by using a uniform kernel, what you see is that we start seeing the objects in a better way. And actually, if you do maximum likelihood again, you obtain cleaner versions of this depth and reflectivity map, but at the price of blurry images, where we lose details around the edge of the objects and we lose information about the small objects in the scene. So the goal is really to combine all these multi-scale estimates to provide sharp and clean depth measurements. And there is a sketch of our framework, how we did this reconstruction. So first we start with this raw data that we assume is a combination of non-uniform background represented in red and green peaks representing the signal. Again, if you do maximum likelihood estimation, this is what you obtain, which is a 3D representation of this scene that you see in the top. Now, the first step of our algorithm is to mix signal from background. After that, we design a robust statistical method to estimate depth and reflectivity. We have an optional step to do Superresolution, and the end result will look like this, which is clean. We don't have these outliers. And actually, instead of estimating only a value for the depth, we are getting a distribution. So we have a notion of uncertainty. For example, if you look at this reconstruction, this point here will have this posterior distribution, which is quite narrow, indicating high confidence. If you look at the edge point, you see that the posterior is quite wide, which indicates that we have higher uncertainty for that point. So let's talk a little bit about the equations. Here we assume that the histograms of counts are denoted by Y, and our parameters of interest are the depth denoted by D, reflectivity R, background P. And we assume that the histograms follow Poisson statistics, that is given by this, where the mean denoted by S is given by this equation. So it's an impulse response of the system denoted by F, which is shifted at the right depth, multiplied by a reflectivity term, and to this we add a bugger. So we don't work directly with this equation. We introduce some approximations that allow us to separate the terms associated with depth and reflectivity. And actually, we see that the depth appears in a Gaussian term, the reflectivity appears in the gamma term. And after that, we also take into account multiscale information by filtering the histograms. And if we assume that the histograms are independent, we can write the approximate likelihood like this, where the scales are denoted by L. So here, this equation is associated with all our cubes at different scales. So this is our approximated likelihood, and we are working with a Bayesian formalism, so we need to introduce prior distributions. And the best way I find to explain it is by using this direct acyclic graph, which is more intuitive. So if here we start with our histograms, which are denoted by Y at different scales, scale 1, scale 2, scale L. To each of these histograms, we have depth parameters associated with them. So D1, D2, until DL. And we want to combine all these depth maps to extract a single clean depth map. For that, we introduce a latent variable denoted by X, where each pixel of X is related to patches of D. And it's related to patches of D through a Laplace prior distribution. So Xn here denotes a pixel of X, and it's related to this patch of the image D, which we denote Dn prime, where n prime move in the neighborhood of n. So in addition to that, we see that we have here some weights denoted by W. These are quite important because we can learn them from other modalities. And actually, you can also learn them from applying state-of-the-art algorithms on these D maps, and then use this information and inject it in our model. So this W here allows us to inject information through the variance of the Laplace distribution here. We note also that we have this parameter epsilon that will represent the uncertainty about the estimated depth. And in our case, we consider a conjugate inverse gamma distribution as it will make our life easy in terms of computations. All right, so this is what we assume for the depth map. Similar things for the reflectivity, except that we consider a Gaussian distribution in this case. Okay, so now we have likelihood, we have the prior, we can combine them into a posterior distribution, and then we want to maximize this posterior. So what we did is a coordinate descent algorithm which update each parameter while fixing all remaining parameters. And we keep doing this iteratively. So the good news here is that to update X, we end up having a weighted median operator, which can be efficiently computed. And all other steps are given analytically. So they can be computed quite rapidly. And this means that the overall algorithm will be quite efficient. So let's see how this algorithm performs in real measurements. So what we did here is that we took our LiDAR sensor and we acquired measurements of a man moving behind these wooden boards at a distance of 50 meters. And in the middle, we have this tent in which we generated artificial vapor. So we took these measurements, and if you look at the raw data, this is what we see, which doesn't show clearly the targets that we have. Now, this is what we have in terms of reconstruction. With the classical algorithm, which is a matched filter, we obtain noisy reconstruction. With our algorithm, we obtain cleaner version together with uncertainty maps, where the blue points indicate high confidence, red points indicate high uncertainty. And you can see that we are less certain around the object boundaries or in presence of smoke in these regions here. So we implemented this in MATLAB. Since the images were quite small, 32 by 32 pixels, we could process 10 frames per second. Now, the strategy can be also applied on multispectral LiDAR data. So we validated this on simulated data. As you can see here, we have our ground truth. in which we have a point cloud, and for each point we have columns, assuming that we sample the data with different wavelengths. And here we have two rows. In the top row, we consider an easy case, where for each pixel, we assume that we have a PPP, which is average photon per pixel, equal to 10. And we assume that the signal to background ratio is equal to 1, indicating that we have as many photons coming from signal and background. So this situation means that we have 5 photons of background and 5 photons of signal. The columns represent different algorithms. This is the classical algorithm. These are state-of-the-art algorithms, and the proposed one is represented in the last column. So you see that in the easy situation, most algorithms provide acceptable reconstruction. Now, when considering the extreme case here in the bottom row, where we have only 1 photon coming from signal and 9 from background in each pixel, you see that all algorithms fail to reconstruct the scene, while the proposed one is able to do that thanks to the multi-scale information. So this shows that the statistical model is able to reconstruct highly dimensional data, whether they are videos or multispectral LiDAR data. When doing an observation of regarding the algorithm, we noticed that it's able to deal with empty pixels. An empty pixel being a pixel that has no photon. And this means that it can be used for super resolution, because in super resolution, we only scan few pixels and we try to fill those empty points in the middle. So we validated this by running an experiment. So we had the Bristol light wave camera, which is a 32 by 32 pixel camera. We did micro scanning by creating sub-pixel shifts, 16 shifts in X and 16 shifts in Y. This means that we acquired 256 shifts. And if you run classical algorithm on this data, this is the ground truth that we obtain. Now, if you only select 10 random frames, you obtain this reconstruction. And if we put this input into our algorithm, we obtain this result, which looks quite close to the ground truth. In addition to that, we can do guided super resolution. Remember the weights that I described previously, which allow us to inject information. So here we did the measurements by taking our sensor and acquiring data at 1 kilometer distance. The scene was a car and a tree. So we used a passive camera, which provides us with higher resolution version of the image, and our LiDAR system here. And by combining the two, we'll be able to reconstruct higher resolution version of the scene. So a nice property also of this statistical model is that if we introduce further approximations, we'll be able to make all updates independent and implement them in GPU to obtain an algorithm that runs in real time. So here, the algorithm is running at 100 frames per second, and we validated it by doing underwater imaging. So here what we have is a scene composed of submarine, some plastic fishes, and here we see from the front using a passive camera. Here we see the scene from the side to have information about the depth map. And this is in the right what we obtain with our algorithms, a point cloud together with uncertainty maps. And actually these run in real time. So as we take measurements, we can do the processing at 100 frames per second. And you can see that we also obtain nice uncertainty maps, indicating that the edges are less centered. Okay, so this shows how the statistical model can be applied to solve different inverse problems while taking into account guiding information. And the next step was to enroll it into a network, as networks are networks, or neural network is quite a hot topic. It allows to solve very challenging problems, and we wanted to see how things work out if we enroll our statistical model into a network. So for that, what we did is that we took our input, we enrolled our statistical model, where we replaced each of the optimization steps by a layer of our neural network. And this means that each layer here is well understood. We know exactly what are the operations happening inside these layers. And this allows us to get as output estimates, but also uncertainty about these estimates. So looking again at our algorithm, here we focus on the depth. And if you look at these equations here, what we are doing is that we are alternating between updates of X and then update of D and so on. And this is what we did here in our network, where we mimicked these 3 steps here. So what's happening within each layer? Well, we start with multi-scale depth maps, and we have squeeze block that take all these multi-scale depth maps and squeeze them into one depth map. After that, we have an expansion block that compares this depth map to all the multi-scale depths and update them using learned weights. And this is mimicking what's happening in the optimization algorithm. Okay, so what kind of results do we obtain with this enroll strategy? Here we show some results on simulated data, the ground truth being represented here. Again, we have 3 rows, moving from easy scenario in the top to very hard in the bottom. The columns represent different algorithms. Classical algorithm in the left is the matched filter, is the maximum likelihood estimator. This second column represents the statistical algorithm I described previously. Third and fourth represent state-of-the-art deep learning strategies. And the last column here represent the enrolled algorithm. So first, note that in the easy case, all algorithms perform nicely. And what we can also see is that the enrolled strategy behaves similarly to the statistical algorithm. And compared to deep learning algorithms, it actually provides better results, where we see that the deep learning algorithms tend to oversmooth the 3D cube and have this bleeding effect, where 2 surfaces that are located at different depths get connected, while with our strategy, they keep being separated. In addition to that, we get our uncertainty maps for free, and these are in quite good agreement with the statistical method I described previously. Other nice properties about this network is that it requires less parameter to train it. And here what we represent in this curve is the number of parameters to train the network versus the running time of the algorithm. And we compare in purple our algorithm, in green the Peng algorithm, in blue Lindell algorithm, which are state-of-the-art deep learning strategies. And you can focus here on the diamond shape, and you can see that while Peng require 500,000 parameters to train, our algorithm only require 40,000 parameters because it's using information from the statistical model. And actually it runs also 10 times faster than this best deep learning algorithm. Another nice property coming from the use of statistical model is that the network is quite robust to differences between training and testing data. To validate this, we trained our network using the impulse response function shown in blue. And then when coming to the testing phase, we changed this impulse response and generated new data. The way we changed it is by convolving it with a Gaussian, having a variance of sigma IRF. So if we increase sigma IRF, the impulse response becomes larger and larger. So if you see in the bottom left image, we are representing the variation of the depth absolute error with respect to sigma IRF. If sigma IRF is large, it means that we deviate more from the training data. And you see that Lindell and Peng, shown in blue and green, deviates rapidly, while the proposed one is quite robust to this shift between training and testing data. And actually, this happens also when the impulse response is asymmetric. As you can see in the right images here, if the shape of the impulse response is asymmetric, it still works. Okay, last point is about super resolution. So can we generalize this network to perform super resolution? And the answer is yes, just by upsampling the weights that we learned in the squeeze and expansion blocks. So we can generalize these blocks by using state-of-the-art algorithms, and this allows us to get the network to perform super resolution. So here I show initial results that we obtained. In the top row, you see what maximum likelihood provide us as depth maps for two different cases. This represented in different columns. And in the bottom, you see what the proposed strategy provides us as super result maps, which are linear maps compared to this maximum likelihood. So to conclude, we have proposed this statistical model that is principled. It can solve different inverse problems, and we can also approximate it to run in real time. We have also proposed this enrolling strategy that works at the interface of Bayesian modeling and deep neural network, and it led to obtain efficient networks. So obviously, this is not my only work. It's a group work involving people working in data processing, my PhD, Amir, postdoc Sandor, Hu, and Steve McLaughlin. And we collaborate with people acquiring data here and industrials. So here I list few papers. If you are interested in the results that I showed today, you can have a look or just email me if you are interested, and we can have discussion. And thank you.
Thank you very much, Abderrahim, for this wonderful talk. Are there questions from the audience? We have several questions. Okay, let's start here.
Yeah, thank you for the talk. So about the work on multispectral LiDAR, I was wondering if you could comment on the extension of that work to the cases where we have colored noise.
To the case where
we have colored noise rather than white noise. The noise that affects different wavelengths differently.
Well, actually, in our data, we have a Poisson noise. So it's affecting differently the data based on their level. So what kind of noise are you thinking about?
Like, for example, pink noise or blue noise. Is it possible to include it in your Bayesian model?
I think so. I think so. It requires remodeling the variances of our distributions. Yeah, it will need some tweaking of our covariances in our distribution to take this into account.
Yeah. Thank you.
Thank you. So next, Rohan.
Thank you. Very interesting talk. I was wondering, so if I understood well, at the beginning of your algorithm, you rely on the histograms of the counts of all the photons. And the histogram can be seen as a sketching technique of the initial data you have. And I was wondering if you could extend your work to other sketchings, like those that are applied by the team of Mike Davis, Michael Sheehan, and others, like the random Fourier features and things like that.
Really nice question. Yeah. Actually, we start from the histograms, and then we project the data into multi-scale depth maps. So in a sense, this is one sketching way of doing things. But I assume you are thinking about what Mike did by using this Fourier sketching. I think, yes, we can try to generalize these methods to this kind of sketching. Right now, I haven't done it, but yeah, it's a really nice thing. I think we can easily do it by using the deep neural network, by starting with projecting the histograms into Fourier domain and then solving the problem in the Fourier domain.
Yeah, because what I think is that basically here the assumption is that you have a regular sampling of your PDF, and there you will have non-regular sampling or regular depends of the characteristic function of your PDF, on which you can also work similarly to what you do.
You mean regular sampling in the TOF axis?
So there are two flavors. Either you do random sampling of the characteristic function, or regular sampling, as the team of Mike did. And here, since you start from the PDF at the beginning, maybe it could be also transparent to that. Okay, thank you.
Very nice comment. Yeah.
Ivo?
Sorry, I sort of had a very naive questions because I've only ever seen these things on the side. So basically everything is called single photon, but then I see a lot of statistics. So I would have expected more like sort of binary kind of images, 1, 0, 1, 0, and so on. So you're having, why is it called single photon in the first place?
It's called single photon because we are using a single photon detector. So
Yeah, but it's not a single photon per pixel, right?
it depends on the system, but usually this for each pixel we are firing a photons, and then we only collect 1 photon per pixel. So if you look at the low level of raw data, you can see that we are acquiring images that are binary, where you have zeros, and in some pixels you detect photons and you detect also their term of life. So if you look at my first image, what we are actually measuring is this photon. You find that a photon represented by its time of life.
Yeah, but you have a whole histogram over here. These are hundreds of photons.
That's related to the question of sketching. So here we are not working directly on the photons themselves. We are sketching them into a histogram. We are projecting them or representing them into these histograms, and then we start working from the histograms.
But would it be imaginable that you do it if you only get a single photon per pixel?
Yeah. So a single photon per pixel means that
I mean, that you just have one entry in this.
Yeah. So if you look at the results I was showing here, so yeah, a single photon per pixel means that PPP is equal to 1. Here I only showed results of PPP equal to 10, but actually, if you look at the bottom row, we assume that we have 10 photons per pixel, but only 1 comes from signal and 9 other are corruptions. So it's more challenging than receiving only one photon. Here we have 1 photon, but 9 obscuring photons at the same time, and we try to mix it. So this situation is more challenging than receiving of 1 photon per pixel.
Okay. And the second point I have been seeing is like usually these pixel detectors, they have like the complicated electronics like that lead to dead times and whatever, like that distort the statistics. And you didn't mention that, even though you are in a Bayesian framework. So I was a bit.
Yeah, true. I assume that we are working in a regime where the dead time is not affecting our measurements. And this can be dealt with when acquiring the data, where experimentalists usually make sure that they receive less than 5% of the pulses that they fire. And if you work in this regime, the dead time effect of the spot is not important.
Okay, thank you.
Yeah.
Thank you for your talk. I just have a basic question. You mentioned that it's an unrolling algorithm. How do you implement, or how do you use the fact that it's an unrolling algorithm in your work?
Yes, so, well, we implemented it by replacing what we had in the optimization algorithm and putting this into a network and then learning the parameters. In our case, the parameters are the weights, these W's that I was showing. So we learn these weights, and then we alternate between updating X and D. So yeah, so here, let me try this. So here we start with D. We learn these weights through a squeezing step, and that will give us X. So X is expressed with respect to D and the weights. And then we also learn other weights that allow us to move from X to a new version of D. And we keep repeating this. And this expansion and squeeze block are inspired from the equations that we had here.
Thank you. I have myself one question in slide 41. The sigma units, are those nanoseconds or what? What is
Now
that?
in bins, I think. I'm not 100% sure,
Can
but
you-
I think in time bin.
Can you convert from bins to nanoseconds from mid to none? Roughly.
It should be mentioned in the paper. I don't remember.
Okay,
exactly
But
the unit, yeah.
that is more in the nanosecond range than in the picosecond range, right? Or approx.
It should be in the picosecond,
Pico.
because if you look at the top, the top picture shows you things in bins.
Okay.
And by convolving with sigma RF equal to 16 or 12, you see it occupying a region of almost. 50,
Okay, so
50
the axis above is also the same as the axis below. It's the same, is number of bins in both plots, right?
Yes, the numbers are the same.
Okay.
So 12 above is the same 12 as the bottom.
Okay, thank you very much. And
Thank you.
please join me in thanking the speaker again.